You are in broadcast.
Okay. First, allow me to thank the organizers. They are doing a great job in every year in putting together this conference. And second, let me look a little at circular economy, because this is one of the things that we really have to look into from various points of view. And I first want to mention, as I do every time that I'm moderating such type of sessions, that, you know, Voltaire, the French writer, was saying that in order to be able to speak 20 minutes and say something about a given topic, you should have worked at this at least 4 years before on that topic. So since our speakers have a great knowledge of the topic that they are talking about, I would ask them to show us that they know what they are talking about by keeping it 20 minutes. And obviously, it's much simpler to speak 1 hour and discuss the topic, but we only have 20 minutes per speaker. So I would like to ask the first speaker to start his presentation. We don't have to wait too much.
Okay.
Enrico Gabriele, the floor is yours.
Sorry, Professor Purica, could I just start me, because I will have the third dose of vaccines in 1 hour, so I just need to start. It's possible for you if I...
Gianluca Carino,
Yes.
you want to start? Okay.
Thank you so much, just because I need to go to make the vaccines in 45 minutes, so I will need to...
So we start with Gianluca.
Thank you.
Okay, Gianluca. Parola a te. Sorry, I'm an ex-Enea, so and ICTP Trieste, so every time I switch to Italian without actually understanding what how the whole thing is actually happening. So let's continue in English. Gianluca Carino, please, the floor is yours.
Okay, thank you so much, Professor Purica. Your accent in Italian is perfect. Thank you so much. I will share the screen. Just tell me if you can see.
That's what I wanted you to do, share the screen with your presentation.
Okay.
I'm shutting down my microphone now, so everybody should.
Could you see? Everyone see? Okay, thank you so much. So good morning, everyone. I'm Gianluca Carrino. Since 4 years, I have the pleasure to work with AIEE, making studies and reports on energy security, renewable energy, energy efficiency, and circular economy. During this analysis, I will focus on the digital economy footprint. Firstly, because the scope of the following analysis will be to recognize the environmental impact of our behavior and our digital habits, and implementing the possible solution to apply a circular economy even in this sector. The data exchanging taking place globally every day has considerable impact on climate change. For this reason, we need to be more responsible and to change our reducing limited consumption and implementing digital sobriety. Going deeply, during this analysis, we are going to focus on the different topics. In the first part, we will talk about the COVID's impact on digital sector, having a focus on the development of smart working, e-commerce, and streaming video. In the second part of the analysis, we will talk about the global energy consumption and the carbon impact for both sector, ECT companies and users, in order to try to understand what are the habits that are not completely clean as we think, obviously digital habits, so in order to understand the mission of digital strategies. And in the last part, we are going to focus on the European 2030 digital strategy goals, having a view of the concept of digital sobriety, that it is a new strategy to reduce the environmental impact. I would like to start the analysis saying that with the global COVID-19 restriction, our reliance on digital technologies increased consistently, especially in the 2020. Therefore, video call, emails, messaging, and virtual entertainment replaced the face-to-face interaction in and out of the workplace. Having a look to the data of the first lockdown between February and April 2020, we registered a global internet traffic around an increasement of the global internet traffic around 40%. Moreover, the user expected to use internet are going to jump from 3.8 billion of the last year to 5 billion by 2025, how AIEE said. For this reason, to achieve the decarbonization global goals and begin the era of the green digitalization and communication, it is fundamental not just to reduce the digital technologies greenhouse gas emissions, but even the behavior of users and companies and ECT companies, and the way of how they consume. Having a look on the COVID's impact, we can say that during and after the lockdown, our life and the role of the internet in our life increased consistently. Starting from the smart working, having an analysis of the Microsoft Teams data, the global user increased from 2 million of 2017 to 145 million in the second quarter of 2021, with an average of around 900 million meetings daily, video calls. So having a look on what is the impact of each video call, we can say that every hour of video call generates around 1,000 grams of CO2 and requires between 2 and 12 liters of water. This means that it's not really sustainable having a video call. And an important point is that leaving the camera off during a conference can reduce our impact, our environmental impact, and the footprint around 96%. Having a look on the e-commerce, we have to say that even the online purchase increased after the COVID, touching the value of 39.4 billion euros, more than 21% compared to the 2020. Last but not least, the streaming videos, having a look on the Netflix data of 2020, in the first quarter of 2020, so the beginning, the first period of the COVID pandemic, the subscribers of Netflix was more than 16 million, and they was polluting for each hour of streaming video around 100 grams of CO2. This means that even the streaming video are not really sustainable and efficient how we was thinking. But how can we reduce our emissions? Looking at a video, we should watch a video in a standard definition instead that an high definition, leading around 86% of the emissions. But having a better look of the smart working, we have to say that if in one hand, it is really positive for the environment because it reduces the employer's travels, so reducing therefore the emissions. In the other side, it not just increases the home energy consumption, but even maximizes the unconditional use of digital channels in order to permit employers to not just work from home, but even to keep in contact with their colleagues. How the graph shows, the actual number of people working from home are around 4.38 million. So this number of people are every day sharing, video calling, and searching messages and info in internet, rising not just the internet traffic, but even contributing in a massive way to the digital emissions. We have to say that all the digital files and information, emails, documents, photos are stored in data centers. And this is a really important issue because the data centers are to be performant, need to consume a really large amounts of energy, contributing to CO2 emissions. So one of the most important goals in the next years will be to achieve 100% of renewable energy, even for this kind of data, for this kind of energy needed for the data centers. Having a look on data in the period between 2010 and 2020, the global internet traffic rised up over 40%, And actually, the digital instruments are producing about 3.7% of the global greenhouse gas emissions. Moreover, the data centers, how I said before, are responsible for, that's because they need a really high quantity of energy. They are responsible of around 1% of the world's energy demand, and we are expected to see a rise and an increasement thanks to the growth of the digital economy and the number of connected users. The energy consumption of digital in the future will achieve the peak between 8.7 and 15.5% in 2025 if we don't use and we don't concretize the digital sovereignty concept. Having a look to the ECT companies, we can say that in the period 2010 and 2020, the purchase of the most important ECT companies such as Amazon, Google, Facebook, and Microsoft was renewable energy. But even if the quantity of energy used in the system are pretty high, matching 100% of annual demand with renewable energy does not guarantee that all the data centers are actually 100% powered by renewable sources all the time. That's because that is linked for the is linked to the variability of the wind and solar that are not matching with the energy necessity data centers demand. But how much we are really polluting when we communicate. Having a look on SMS, for each SMS, we produce around 0.014 grams of CO2, and it looks the most sustainable way to communicate, but it is dying out in daily use. Having a look in the internet search, for each Google search, we produce around 0.2 grams of CO2, and it is a really important value because if we consider that every day around 3.5 billion of people make a search on Google, at the end of the year, for each users, at the end of the year, each user produces around 80 kilo of CO2 per year. So even internet search and Google are not really sustainable and efficient. Having a look on the email, if we send a normal email, we will, for each email, we will produce around 4 grams of CO2, but these emissions will increase when we'll attach the files, the documents or pics, producing 50 grams of CO2. Obviously, this is not really important, but if we consider that every day we send to work around 300 billion emails, this value will be so high. In fact, we will produce around 1,200 million tons of CO2 for the total number of email. So this is so that even sending email is not really efficient and sustainable if we don't use renewable energy, and if we don't reduce their use, such as the thankful emails or all the email that are not fundamental to send. This graph shows just the number of sent and received emails per day. How can we say from 2017 to the prevision of 2024, they will increase around 34.42%, from 2,069 million to 36,100.6 million of sent and received email. And the level of emission related to those emails will increase consistently if users don't change their way to communicate, and if data centers, how we said before, doesn't purchase 100% of renewable energy. Having a look of the nature of data transmission, we have to say that they are changing rapidly from desktop to mobile. In fact, the mobile device traffic increased in the last years around 50%, and the laptops and desktop computers around 17%. This shows that the way to be digital and to connect are always more and more. Just this because we have always our telephone on our pocket, and we can do search and send email messages and use social when we want, contributing in a consistent way to the climate change and to the emission. Having a look on the 4 and the 5G, we have to say that the 4G networks are more efficient than the 3G, 5 times more, and 50 times more than the 2G. Having a look of the 5G, this new technology will be more efficient than the 4G, around 10 or 20 times, reducing the impact on the environment. Having a look on the European 2030 digital strategies, we have to say that in January, European data centers operators and industry associations launched the Climate Neutral Data Center Pact, which focus on 3 important targets considered like such a core in order to achieve the decarbonization goals. The first one is to achieve the climate neutral navigation, where ECT industry are agreed to reduce their emissions around 45% before 2025 and to achieve the total climate neutral and using renewable energy in 2030. The second core target is the highly energy efficiency, where users and ECT should reduce their energy waste, implementing awareness on digital sobriety. And last but not least, the sustainable data centers, where center electricity demand should be matched in 2025 by 70% of renewable energy and 100% in 2030. But what is this digital sobriety? Firstly, we have to say that with digital sobriety means to avoid the digital consumerist, incentivize not just awareness on the way to be responsible and conscious implementing, on the way to implement an attitude that is responsible and conscious towards digital tools, but even using more efficient, sustainable digital tricks, such as having a look on the smart working, exchange of office documents on a shared platform, but even, for example, reducing the use of video calls or reducing the definition of streaming video. For example, in a video conference, like the video conference that we are doing now, whose participants, so where participants are located in different countries, could alone produce up of 2015 kilograms of CO2 emissions. And this is so interesting because the energy consumption of video conferences is high. Using this software to replace travel by car, train, or plane means saving on average of 93% of emissions. But how the ECT companies, so the information and communication technology companies, are investing to reduce the risk and the impact on the environment? We will do some examples. For example, in the side of Ecosia is planting a tree for every 45 searches it performs. This is a sort of carbon offsetting that help to remove the CO2 from the atmosphere, respecting the decarbonization goals. From the point of view of Google, it wants to achieve carbon-free energy all day long for all day week in 2030. And Facebook, not just create a new climate science information center with the goal to be in line and to aware people giving information on climate change, but in the other side, even achieving the zero net emission in all supply chain and even in indirect emission, relying and investing on technologies that absorb CO2 emissions from the air. We are going to conclude our analysis saying that the digital pollution includes all the sources of environmental pollution produced by digital tools. So if in one side we find the first all the problems related to the manufacture of any digital tool. So we link to the concept of circular economy, all the raw material that we need in order to produce digital tools, but even the functioning of the internet. So we will have two kinds of possible solutions. In the side of the ECT companies, they should invest and be more efficient and sustainable, implementing renewable energy. And on the point of view of the users, they should concretize the concept of digital sobriety, implementing efficiency and circularity, even in the digital sector. So from the point of view of the ECT, they should measure consumption in order to have shared metrics, but even declare which sources they feed on. with the goals to achieve in 2030 100% of renewable energy, even for the digital sector. From the point of view of the individual users, they firstly need to change device less frequently in order not just to reduce the supply of the raw materials, but even to implement the principle of the circular economy, and to reduce the demands of the raw materials that are considered as dangerous and not really that we find in with a really linked geopolitical problems. Avoiding compulsive avoiding compulsive use of digital channel, for example, sending video, images, and audio. So reducing the attitude to be always in touch, and don't keep unused apps that update continuously. Thank you for listening. I would like to finish my presentation with these sentences of George Westerman that say, when digital transformation is done right, it is like a caterpillar turning into a butterfly. But when done wrong, all you have is a really fast caterpillar. Thank you for your attention. And it's always a pleasure to be part of this symposium.
Excellent. Thank you again. You were perfect in timing. And first, I want to make a comment. Actually, you've been discussing one of the very interesting intercorrelation between the two greatest machines that humankind has made, energy system and the information technology. And I remember that I have a friend that is a director for distribution in an American power company in USA. And he was talking about the fact that one big IT company in the States was making computer storage center there. And you know, these things are consuming a lot of energy. That was a good thing for the power company because the company was paying the energy. But the idea is that they choose that power company because most of the energy that they generated was coming from hydropower plants. Conclusion, the trend that you are describing is actually real. It's happening. Consuming energy, consuming renewable energy for the IT components of the world. Actually, cryptocurrencies are now consuming a lot of energy, and it seems that they also have a trend to reducing emissions. Anyway, thank you a lot. Are there any other questions from the other speakers in this? If they are not, then thank you a lot. It's been a refreshing presentation about the future and the trend that is catching on and enlarging in the world. Good luck with your research, and we hope to see you soon as a professor in these topics, and all the best then. I'm kindly asking the second speaker, Professor Enrico Gabriele from Lunta University, to join in. Hello, Enrico. It's a pleasure. LUMSA is one of the active universities, and I would like to thank you for participating and sharing with in this conference some of your research. Please, it's your turn to start the presentation.
Thank you very much, but the turn belongs to Mr. Komiyama. Now it's time for Komiyama. I come in third place. So, floor is yours, Mr. Komiyama.
Yeah, sure.
Okay. Yes.
Professor Komiyama, you are going to make the presentation?
Yes.
Okay, it's a great pleasure. Then you start the presentation. Tokyo University is present in here, and I remember with great pleasure my time in Japan on a conference of renewable energy and emissions and climate change organized by METI, where I was invited as a presenter for Romania. So allow me to thank you in advance for your presentation. Domo arigatou gozaimashita, Komiyama sensei. It's always a pleasure. Japan is very active, and I remember I was doing a lot in the Kyoto protocol.
Yes.
So please start your presentation. You have 20 minutes. Thank you.
Thank you, Mr. Chairman. Kind introduction. I'm very glad to hear about your Japanese experience. So, and thank you again. And my today's presentation title is the installable potential of small modular reactors and the renewable energy for achieving carbon neutrality in electric power system. The topic is three topics. First is introduction, Japanese energy policy, renewable energy, and the small modular reactor. And my today's emphasis on the analysis by optimal power generation mix model. This is an energy model analyzing, allow us to analyze a power system overview and scenario and the result, and wrap up by conclusions. First, this is a Japanese greenhouse gas emission reduction strategy. So Japan pledged 46% reduction by 2030, and the pledge net zero emission by 2050. Very aggressive to deeply reduce the carbon emission, greenhouse gas emission. But still, the more than 80% of greenhouse gas emission in Japan is a carbon dioxide emission. So we have to maybe achieve energy transformation, energy transition by 2050 to achieve carbon neutrality. And it requires the accelerated adoption of clean energy technology across entire energy sector is very significant for achieving carbon neutrality. So this is a Japanese target of power generation mix by 2030. So METI, Ministry of Economy, Trade and Industry Japan, now formulate the Japanese power generation desirable power generation mix by 2050. So maybe this Japanese METI's policy now focusing on first, maximization of the fraction of renewable energy. The fraction is 36 to 38%. Currently in Japanese renewable fraction is 80%. So by 2030, for nearly upcoming 10 years, maybe they enhance up to 36 to 38. So almost a double of the fraction is expected. And the other simultaneously, Japanese ministry now aims to back maybe the recovery of nuclear power plant after Fukushima nuclear accident. Now, majority of the Japanese existing nuclear power plant is now maybe the stranded, maybe the suspended. Output is suspended. Now, fraction is 6%. Is maybe the expected to be recovered to 20 to 22%. So probably this renewable and the nuclear is a very important option to decarbonize the Japanese power sector by 2030. And also Japanese METI now plan achieve the plan of carbon neutrality by 2050. So currently Japanese carbon emission is nearly 1 billion ton. So by 2050, maybe the Japanese government pledge achieve a carbon neutral, so zero emission, both in electricity sector and the non-electricity sector. So simply saying the Japanese carbon neutrality strategy is first electrification, and the second, the promotion of clean fuels, and the third is CCUS, carbon capture, utilization, and the storage including a negative emission technology. And maybe even in 2050, maybe some sector continue to use a fossil fuel. In order to cancel out carbon emission from this fossil fuel, maybe utilize a carbon removable option, such as a plantation or a negative emission technology like ducts. First, on the renewable energy. So compared with the European countries, Japanese, maybe the renewable energy is not so much right now. Maybe the current maybe the fraction of renewable energy total is nearly 20%. But as you know, Germany, United Kingdom, and Italy is almost achieving the 40%. Maybe they are compared with a European country, still maybe we have a bigger opportunity to promote renewable energy. But kind of the Japan now are ongoing on the experience rapid growth of renewable energy right now, particularly solar PV is rapidly growing right now. And the Japanese current total solar PV installation is maybe the number 3. First is China, second is the United States. Japan is number 3. But in terms of solar PV installed per land area, Japan is number one because Japan is a very small island. Japanese land area is very small, but the solar PV capacity installation is already number 3. So maybe installed per land area already number 1. So we already have enough maybe the solar PV installation. And the next is a small modular reactor. So as you know, maybe conventionally, maybe many countries install maybe large-scale nuclear power plant. Large-scale nuclear power plant definition is more than 700 megawatt. So, but the right now, maybe the many countries is very keen to develop small modular reactor. The definition of a small modular reactor is in terms of a capacity up to 300 megawatt. So maybe the small meaning physically a fraction of the size of the conventional nuclear power reactor. Maybe the second point, module, maybe the meaning of a modular is a very important meaning. Making it possible for system and the components to be factory assembled and transported as a unit to a location for install. So probably this maybe the feature of a modulation maybe allow us to maybe the reduce the construction cost of nuclear power plant. So maybe in the next slide, I'd like to simply maybe explain the feature of a small modular reactor, SMR, compared with a conventional large-scale reactor. In terms of a construction cost, SMR, maybe the investment can maybe the obtain investment risk reduction. Maybe per one unit, maybe the order of the money is hundreds of millions. But as you know, large-scale reactor, maybe already United States and Europe, some Nordic countries experience a soaring construction cost. And the construction process, maybe in SMR, maybe we can expect shorter construction period and the payback period. But as you know, large-scale reactor, maybe they face a risk of a prolonged construction period of the explicitly observed in the United States and the European countries. And the safety, this is a very important in terms of public acceptance. As you know, SMR has a passive safety. Safety is very high, but as you know, large-scale reactor already experience increased cost for ensuring a safety. And the accident risk, as you know, SMR, maybe the uploading nuclear fuel is very small. So eventually, maybe the SMR has a limited evacuation area in case of a severe accident like Fukushima. But as you know, large-scale reactor, maybe the require vast evacuation area in case of an accident like 20 kilometer or 30 kilometer, something like that. And the significance and the challenge of SMR, maybe we can have an expectation for the development of the nuclear industry and the decentralization of electric power system and the inheritance of technology. But maybe there is some kind of disadvantage, kind of economies of scale. Maybe the mass production and the proficiency effects can be expected or not. And also maybe the SMR, maybe one of the advantages, nuclear heating can be utilized. Nuclear heating is expected for decarbonizing, particularly for non-electric sector like industrial process. So maybe the depends on the type of reactor. Maybe the small modular reactor can produce a very high temperature heating. Maybe the to 300 centigrade to nearly 1000 centigrade. Maybe this kind of a high temperature heat can be used in the, for example, in the hydrogen production, and maybe the heavy oil desulfurization, petroleum refining, methanol production, paper pulp manufacturing, coal gasification, and steel making process. So maybe the SMR is expected to play a role to maybe decarbonize a non-electrical sector as well. And Japan has already have one maybe a high temperature. Already we have a test reactor of a small modular reactor. It's called the high temperature gas cooled reactor. One of the already in Ibaragi Prefecture, Tokai village in the Ibaragi Prefecture. And one of the maybe this Japanese test reactor, HTGR reactor, has kind of the technically possible to produce kind of very high temperature heat. Temperature is nearly 900 centigrade, and eventually that high temperature heat can be utilized to produce a hydrogen. So maybe this clean hydrogen is expected to decarbonize a non-electrical sector. And also maybe this Japanese HTGR has several multiple feature enhanced safety, load following capability, very harmonizing with solar and wind power, variable renewable energy, and also a multiple purpose use of nuclear energy, electricity, heat, and hydrogen. And also maybe the United States and new scale small modular reactor is now maybe actual planning is ongoing, and also Japanese kind of the Hitachi nuclear energy or also plan to maybe build two types of a small modular reactor. This is a light water reactor, and the very high, has a very strong cost competitiveness comparable to gas-fired power plants. And also Hitachi also now plan to build a fast reactor. Fast reactor is very efficiently reduce the volume of a high-level radioactive waste. And also maybe this high temperature eventually allow the very high thermal efficiency, and eventually improved, maybe the efficiency is improved compared with a conventional light water reactor. And maybe this is one of my plan to utilize, place three types of small modular reactor in whole energy system. So some of the small modular reactor can produce a very high temperature heating. So maybe this very high temperature heating can be utilized in maybe for example in the produce a very clean synthetic fuel, including hydrogen and carbon capture and utilize and storage CCUS technology. Maybe this synthetic fuel is maybe utilized in, for example, a vehicle or industrial process. And maybe this synthetic fuel is combusted in this kind of end-use technology, emitting maybe a carbon dioxide into the atmosphere. But it can be maybe collected again, carbon dioxide from the atmosphere. Maybe this kind of a carbon, maybe this kind of a small modular reactor can maybe contribute to achieve a carbon recycle. Also, maybe these kind of new types of utilization can be possible in small modular reactor technology. So my modeling analysis research objective is assess optimal integration of a small modular reactor into a Japanese power grid under carbon regulation, and the identification of the best installed capacity of a small modular reactor in the Japanese grid, so as to minimize power system cost and to fully decarbonize the power supply in Japan. And we developed this kind of a power grid model. The feature is a very detailed geographical resolution and the high temporal resolution, and consider the 19 types of power generation technology. And in this modeling analysis, maybe we assume a small modular reactor SMR building in the site of an existing Japanese coal-fired power plant. And this analysis assume small modular light water reactor types of a small modular reactor. And this is a major assumption about the nuclear energy, large scale conventional reactor. We assume a fixed value assumed in 2050. And the small modular reactor in this modeling analysis determined by optimization. And about the nuclear power generation, and together in the large scale reactor and the small scale reactor, in this modeling analysis limit 20% of total power generation in Japan, complying with the Japanese power generation mix policy. And SMR technical data, assuming construction cost is $5,000 per kilowatt, and assuming a load following constraint and the minimum output constraint, and assuming carbon emission constraint. In this modeling analysis, we assume a carbon neutral. That means that the carbon emission is 0. So we maybe implement a nine scenario analysis. And in all scenario, we assume that the carbon emission from power sector is 0, carbon neutral. And this scenario analysis mainly focusing on the SMR consideration and SMR cost and the hydrogen cost and the renewable energy output curtailment and SMR flexibility. And this is the result about the power generation and the capacity mix. So the feature of the result is first is SMR is deployed in all scenarios considering SMR. So maybe the computational result suggests that the SMR is economically rational option for decarbonization. And focusing on large scale reactor and the small modular reactor. So maybe in all scenario, SMR is deployed. So, and also maybe in some scenario, assuming kind of the cost reduction cases, much more SMR can be introduced. So maybe the increased deployment by lower construction costs can be expected. But in case of a large scale nuclear power plant, conventional nuclear power plant, particularly when the SMR is introduced, large-scale nuclear power plant power generation is decreasing. So large-scale nuclear reactor decreases under extensive integration of renewable energy, because large-scale nuclear power plant output, maybe operation is very inflexible, very hard to maybe flexibly control the output in case of a large-scale nuclear power plant. So maybe the large-scale nuclear power plant is not so much harmonized by variable renewable energy. So probably under the massive extensive integration of renewable energy, maybe SMR is a very important option for maintaining nuclear power under massive renewable energy integration. And this is the actual maybe optimal power dispatch in scenario 1, maybe the month in May 1st to May 31st. And the maybe this chart showing the large-scale nuclear reactor operation as observed. Maybe a large-scale nuclear reactor, maybe they are doing base load operation, not flexible. But in case of a SMR, small modular reactor, when solar PV is maybe the output increasing, maybe in order to absorb this solar PV output, maybe the small modular reactor reduce output, suppress this electrical output. So maybe in SMR, a flexible operation is observed when renewable energy output, like solar PV, increases. So maybe SMR is maybe technically harmonized with variable renewable energy. And in terms of a total power system cost, in the scenario 1 to 6, when SMR deployment is observed, is lower than scenario 7. Scenario 7 is no consideration for SMR. So eventually, SMR contributes to reduce a total power system cost in achieving a carbon neutrality. So conclusion, so maybe we develop maybe the energy power system model considering the small modular reactor and the variable renewable energy, and the results suggest that the SMR is significant for both enabling massive variable renewable energy integration and achieving carbon neutrality of power system in a cost-effective manner. So thank you very much for your kind attention.
Thank you so much, Komiyama-san. It's been an incredible presentation on future. Let me do some mentioning. First, Romania has recently signed an agreement with NuScale to build a 6 units power plant on the site of some old coal-fired power plant. And that is ongoing. Second, it's a great pleasure to announce also that in Romania, together with Ansaldo, we are developing a lead-cooled fast neutron small modular reactor that is actually intended also not only for the generation of heat and power, but also for using the waste fuel from our CANDU power plants to diminish the waste quantity by extracting more power from that waste fuel. So it's a great pleasure to see that Japan is on the same track. And I was very impressed when we visited Japan to see that there are a lot of interesting initiatives there. I only mentioned 2 of them that I saw. First, some wind power plants on the shore of the Pacific, where the wind was very strong. And they were controlled by internet from a central facility. Second, we visited Nippon Steel outside of Tokyo, and they were, I'm talking 10 years or almost more than 10 years ago, they were stocking hydrogen from the steel making process, because they said in 20 years time there will be fuel cell cars that will actually need that hydrogen. So I'm very much impressed by the 50 years plan of development in Japan, which is not very custom in Europe or in the United States. They are usually going for semesters or at least 5 years, not a larger period of time. Again, thank you so much. Domo arigato. And it's a pleasure. Any other questions from the audience, from other presenters? If not, then thank you again. We hope to keep in touch on development of these things. I was involved in nuclear. I'm a nuclear engineer, basically. My career started by building nuclear components for the CANDU reactors and things like that, with quality assurance and other things. So then I went out to do economics of nuclear. So it was a really interesting thing. Thank you again, and let's pass to the next speaker. Actually, the last speaker of today, Professor Enrico Gabriele from LUMSA. I hope he's still connected.
Yeah, I'm online. It's
Ah,
not
perfect.
a PhD candidate, but I take it as a goodwill of becoming one day, hopefully, a professor. But
Okay. Thank you, sir. We're waiting for your presentation.
Okay. Perfect. Do you see my shared screen? Okay. And I start. This research consists of a macroeconomic empirical research as part of my PhD research project, which finds some empirical evidences of a circular economy, if properly detected, and some instruments which are typically considered as capital intensive, in this case patents and industrial designs. In particular, what makes this paper, I hope, interesting is the fact that this is a the scale of arguments that I am talking about in this lecture. Is that the circular economy is a relatively young branch, because so in other terms, it still does not have a universally accepted definition of it, but as we mean that a universal definition will mean an easy instrument to measure, to monitor in quantitative terms a phenomenon. There's no even a school of thought which does not provide any kind of a definition, and in turn instrument or a parameter to be measured. So my efforts consisted of finding and challenging these limits, overcoming it, and to find some instruments, some econometric tricks to measure a circular economy. I based my researches on some of the most recent literature from Kircher et al., Polting et al., which are peer-reviewed journals, in this case, journal Cleaner Production by Elsevier. And I adopted for a macroeconomic scale data from Eurostat, in this case, a Sankey diagram, which studies in detail the flows. Capital intensity, in this case, is the most proper parameter to measure the goodness of effects of patents and industrial designs, in place of simply computing industrial designs and the number of applications as a total amount. In particular, what makes this research particularly, okay, seems to be locked, okay. As a premise, I must tell you that circular economy created some perception numbness, because some people could be quite could be confused by the heterogeneity of definitions from both peer-reviewed and non-peer-reviewed. Macroeconomic empirical evidence is in turn even more difficult to be detected, but this paper is capable to do it. In order to do it, I just followed the reference to the Sustainable Development Goal now 11.6 from the United Nations, which stated that we must reduce the adverse per capita environmental impact of cities, including by paying attention or air quality, municipal and other waste. This is coherent to the spirit of what I found out. In particular, patents better worked to increase the recycling rates, and industrial design designs better work to reduce the total tons of waste disposable in landfills, incinerators, recovery for energy. Okay, then what I can tell you is that patents better work for recycling rates to augment recycling rates because they unlock novel inventions, novel functions, or new kinds of materials that can be used or that are more proper to be used for recycling because they are easier to be recovered or to be recycled. Industrial designs preserve intellectual property of aesthetic, not purely utilitarian features of products, which make them more comfortable and long-lasting in their usage, so that it is possible to prevent a product from becoming a waste per itself, or make it more long-lasting, more efficient to use. What makes convenient to evaluate from a macroeconomic perspective is that it is well known that both patents and industrial designs produce a spillover effect throughout an economic system of a country, of a nation, and in turn this questions me for a research from a macroeconomics perspective. It is also well known that the higher the GDP and the more the number of total applications of patents and industrial designs. Therefore, to make it more challenging, I used an adjusted ratio in place of total amount per se. So I used the two indicators of capital intensity, which even takes into account whether a country is more capital intensive than another, in place of confusing the two dimensions. Okay, and in particular, we will see that in case of industrial designs, such evidence does not belong to the entire Europe, but to a selected number of countries, which we call the EU inner six countries. The historical countries which agreed on carbon, steel, and atomic energy power generation. And so that's to say that they shared and started from a particular expertise, which led to the convention of the Hague Act in 1960 as a premise to where to start from, and then to experience in different fields such expertise. So this is essentially the scheme of how it works, because it starts from the linear economy, and then gradually reaches the fully circular economy, where the level number one consists of the tools I use to compute the recycling and recovery rate. And the two other dimensions, including some strategies from the 9R framework as adopted by the Dutch government, suggesting me to suppress the dimensions into extended lifespan of products and its parts, and smarter product use and manufacture. It is still impossible to distinguish the two dimensions, level 2 and level 3, simply because, as EXPRA told us, there are too many legal systems and too many differences among the European countries. 10 legal different frameworks are enforced in relation to extended producer responsibility and return on waste generation and on its reporting. But however, it is interesting to measure it from an econometric perspective, as a suggestion, as a hint on how to deal with waste management for future policy making. So we can see that the level 1 cycle rates belong to the closest sorry. It refers to the most basic strategy, level 1 recycling rates, while the other two ones belong to a more refined, more complex, more sophisticated strategy, because it could even avoid from being reported. We might not be aware of it. So therefore, I used an econometric trick. In particular, what compelled me to use a structural back in case of industrial designs, as Figure 1 and Figure 2 demonstrate, consists of the fact that the inner countries have a structurally higher capital intensity in terms of industrial designs. While in case of patents, this evidence of this structural break does not exist at all. And so, in order to have the power model, I compared these compounding features against control variables which have been detected by a very recent research by Aguilar and Hernandez, which I found out, I recognized into per capita income, employment of population, and renewable energy consumption. I will be brief, essentially, because the results are this one, so you can see. Simply because recycling and recovery rates are linked to environmental patents, environmental technology patents on environmental technologies, and they are a very good predictor of this strategy, while control variables are absolutely negligible because they work better for long-run projections. And indeed, we talk about circular economy as a young branch. Otherwise, we would have a macroeconomic model. And this is not possible nowadays because we expect the circular economy to better work for future policy making and not for present ones as we are experiencing nowadays. That industrial designs and patents worked very well. In case of total bed disposal waste, an indicator created through principal component analysis is better predicted by inner six the inner six countries and industrial design interaction term. To say this is the most likely evidence to explain why in the total bed disposal waste has been declining, and it is imputed to both mostly to industrial designs and to a lower extent to enforcement, to enlargement of deployment of renewable energy sources. In this case, I must be clear, renewable energy are referred to electric power generation, transportation, and heating. And that's, it's essentially an econometric evidence that must be further analyzed, but it is some of the most recent evidence we can see, because other papers did not afford it and had some difficulties to conciliate intellectual property rights or to distinguish the dimension of intellectual property rights from effects of circular economy, because most of the researchers tend to overlap the two dimensions, while this research wants to highlight that the two dimensions are not overlapping, but the one is the cause and the other is the effect. And I hope to extend the research to find more accurate indicators for future researches. And that's all. If there is any question, it is welcome. I am available for any question you might think to do. Thank you very much.
Thank you a lot. It's been a very interesting presentation, especially since we are talking now about the impact of innovation, and circular economy is actually a question about replacing old, non-efficient, polluting technologies with innovative ones. And I can say that because I am a member of the Prime Minister of Romania Advisory Council for Sustainable Development. And we are developing all sorts of potential analysis. And thank you for the one that you made, related to putting out a map of risk at every region of Romania for climate change events. I done that when I was working in ENEA for Italy, for example, and if you're interested, we can share some information. Also, doing some analysis of nonlinear impact of innovation, and that is something that check my name on Amazon. You will find a book on nonlinear models. This is important because I think that what we are doing right now is a shift of paradigm in all economies, not only in energy. And energy is more important, information is important, but there are various other fluxes of money and products and labor that are actually making an economy work. So it's interesting that innovation is something that is very important for this. Thank you again. And I think we are close to shutting down. Other questions from the participants? If not, then this is it. Thanks again for your participation, and let's keep in touch through the Italian Society for Association for Energy Economy, and even through LinkedIn and various other methods. We are now almost at Isaac Asimov Solaria planet. We are starting to communicate electronically, and I hope we will not be arriving at the level when we cannot meet physically because we do too much electronic communication. Anyway, thanks a lot for all the presenters and the participants, and thanks you, Associazione Italiana de Economisti per Energia, for organizing such a great conference. And this is it. It's always a pleasure. I hope the presentation will be on site. All the best then to everybody. This is the end of our morning session, and good luck with your research. And it's always a pleasure to be here.
Okay.
Thank you very much.
All the best, everybody. Thank you. Grazie, arigato, and I all the best. Bye.
Bye.
Thank you so much. Bye.
Bye-bye.
Bye.